for 2 hours.
Okay.
Looks like we have to cancel class.
So here my A is a given matrix. This is just an example, right? But now I switch row 2 and row 3. Then, if I wanted to find the determinant of B, I would just take the negative of the determinant of A, right? So if I went through the whole trouble here of doing Laplacian expansion and going through all of that, and I get an answer, and then I ask, what's the determinant of this one? You don't have to do Laplacian expansion and go through all that answer again. You just realize that you switch 2 rows, you just take the negative of the original answer.
So you can also switch the third and first row and you negate that.
Any 2 rows, right? So if I had switched the third and the first, I would still be the negative.
Could you switch columns?
Yeah. It would also work.
It would negate it also?
Yes. Determinant's sort of weird. If you do column operations, you can actually talk about determinants because determinant of A transpose is equal to determinant of A. But in general, column operations are sort of illegal. You want to stay away from them.
So, okay. And
right. Switching any 2 rows or columns, you negate the determinant. That's what the first theorem says. Right? So if you realize one matrix is just switching 2 rows of another matrix and you already know the determinant of that, you don't have to recompute the determinant of this. Right? That's the first theorem. That's theorem 1. Theorem 2. So by the way, note this is a type 1 operation. Right? So this theorem could be rephrased in the sense that performing a type 1 operation on a matrix negates the determinant. Right? Theorem 2. Let A be a matrix. B is obtained by multiplying one row of A by a scalar K, then the determinant of B is equal to K times the determinant of A. Right? So if you multiply a row by a constant, the determinant has to be multiplied by that constant.
So it's linear.
So, for example, determinants are not linear, no. What? No, they're not linear. Example, come again?
No. I mean, if you multiply the whole thing by a scalar, then it's C to the N, right?
Right. Yeah, so, which we're going to get to that theorem. It's not linear. This is not a linear thing because you're only multiplying one row. So example, if A was, again, 1, 2, 3, 4, 5, 6, 7, 8, 9, and B equals 1, 2, 3, 4K, 5K, 6K, 7, 8, 9. Determinant of B equals K times the determinant of A. And this K could be anything, right? Any constant, right? So if you want a concrete example, 1, 2, 3, 4, right? Let's say, what's the determinant of this guy?
Minus 2.
Minus 2, right? 1 times 4 minus 2 times 3. That's 4 minus 6. So this is actually minus 2. Now let B equals, if I multiply the top row by 3, 3, 6, 3, 4, then determinant of B is just equal to 3 times minus 2 equals minus 6, right? And if you actually do it the long way, you'll see that's what you get, right? If I multiply any one row by a constant, multiply the determinant by the constant, it gives me a new determinant. I don't have to actually recompute it.
Doesn't matter which row.
Doesn't matter which row, right? As long as it's a single row, if you multiply any one row, doesn't matter which one, by a constant, you have to multiply a determinant by that constant. So that's the theorem.
What if you multiply two rows by a same constant? Then it'll be squared,
Yes.
and so on and so forth.
And so on and so forth, which in fact leads to the third theorem. Which you can think of as a corollary. I always forget if it's 2 R's or 2 L's. Corollary. The determinant of k times a is equal to k to the n times the determinant of a. Right? Remember, my n is still the number of rows. Right?
Okay.
But remember, ka means you multiply each row by that scalar. Which means, according to that theorem, I'd have to factor out that scalar for each row. Well, there are n rows, that means I have to factor out n k's. I would get this guy. So, for example, we know that, again, if a is equal to, let's do a simple example, 1, 2, 3, 4, and we know that the determinant of a is minus 2, then, if someone asks me, what is the determinant of 5a, right? You don't have to actually find 5a and then find the determinant. You just know that this is just going to be equal to 5 times minus 2. What's the power of here? 2. So this will actually be 5 squared times minus 2, which is 25 times minus 2 is minus 50.
What is the long way?
The long way would actually be to find 5a, which would be 5, 10, 15, 20, and then you do the expansion, right? But this is a 2 by 2, that's easy. I mean, if I had a 3 by 3 or 4 by 4, then actually multiplying all those guys by 5 and then doing a Laplacian expansion is going to be a huge mess. This actually cuts down the work for you. Because we know that's true, then this will have to be true, right? Because if you put a scalar in front of a matrix, it means you multiply each row by it, and then you pull out a constant for each row. So it's just that scalar time raised to the power of the number of rows times the old determinant. So that's another important theorem. Let's see another example. So you have a 3 by 3 matrix, and pretend you actually did the expansion, you found the determinant was 5, right? Let's pretend that you actually did that. So my example is find the determinant of 2a. So these theorems are so powerful that you don't even have to know what the matrix looks like. If you know what the determinant of the original one is, you can figure out the determinant of any multiple of that matrix. Tell me the intermediate steps.
2 to the third is 8 times 5.
2 to the third times 5, right? This guy here is the number of rows. This guy here is the determinant. Right? So according to this formula, it's the scalar raised to the number of rows times the original determinant, and that's what we're doing here. So that's just 8 times 5, it's going to be 40. So once I know the determinant of a matrix, I know the determinant of any scalar times that matrix by this formula. Right? I don't have to actually compute the new matrix and actually re-expand. Right? It's just a waste of time. We saw this before. But I'll just re-say it. Theorem 3. Type 3 operations. Do A equals 1, 2, 3, 4, 5, 6, 7, 8, 9, and B equals 1, 2, 3.
Could you just do a 2 by 2 matrix?
Huh?
6 space.
Doesn't matter. So let's say here I get row 2 minus row 3. Right? So I do 4 minus 7, I get minus 3. I do 5 minus 8 minus 3, I get 6 minus 9 minus 3. Then determinant of A is equal to the determinant of B. Because I obtained B from A by doing a type 3 operation. The determinant's not going to change. So if I know the determinant of this guy, it's actually going to be the same as the determinant of that guy.
Actually, with that one, we have a negative 3, negative 3, negative 3. Would it be possible to factor out the negative 3 in that row, find the determinant as if it was all ones, and then multiply by the negative 3 at the end?
Yeah, you'd be applying the previous thing.
Yeah.
Sure.
Is that often useful or no?
Not if you already know what that guy is.
No, but if we don't know, then...
Yeah, sometimes you can do that. But notice that you would be applying one of the previous theorems.
Yeah, obviously. Yeah.
Okay. So this is just an example. If you do any type 3 operations, it won't change anything. The determinant remains the same. Theorem 4. Determinant of A is equal to the determinant of A transpose, right? Example. Right? Once you find a transposition, it's the same, right? And the thing is, that's true because Laplacian expansion, you can do it against rows or columns. So doing an expansion along the first row here is equivalent to doing an expansion along the first column there. It's not going to make a difference because you can choose row or columns.
Should that be R2 plus R3? Right.
No, R2 plus R3 would be different. That would be 4 plus 7. Okay.
I have a question.
Yes.
What if you multiply 2 rows by 2 different values?
Then you take the determinant times one value times the other value.
Okay, that works.
Okay. So transposition doesn't change the determinant. They gave you this theorem even though they never told you what it was. But let me mention it anyway for when we get to the next chapter. Determinant of A inverse is equal to 1 over the determinant of A.
Isn't that obvious?
It's not so obvious. It's something that had to be proven. It's not obvious if you don't know what A inverse means, right? We will see that A inverse is the matrix such that A times A inverse gives you the identity, or A inverse times A gives you the identity. And using that fact, you can actually derive this formula. And you can derive that formula because of the next property. The determinant of the identity matrix, I believe I told you this before, is 1, right? Because it's a diagonal matrix, just multiply along the diagonal. Right, so with that property, so we see that 1 is equal to the determinant of In, but that's just the determinant of, well, I have to actually tell you another theorem. I'll probably just prove it in the inverses chapter when we actually start talking about inverses. Right? That's the next chapter. We're going to talk about this. I don't know why they told you in this chapter. But yeah, the inverse, and we'll figure out what that means. He's a really slippery guy. He doesn't always exist, by the way. In particular, if the determinant of A is 0, then this equation doesn't make sense. He won't exist if the determinant is 0. We'll talk about that in chapter 5. For now, let's move on. Property.
But wouldn't the inverse of the zero matrix be just the zero matrix itself?
No, the zero matrix has no inverse. Because there's nothing that you can multiply 0 by to get the identity.
Oh, I'm sorry.
Anything you multiply 0 by, you get 0.
Yeah, obviously.
Right, so the 0 doesn't have an inverse. Property 2. If any row or column of A has all zeros, then determinant of A equals 0, right? We can just do Laplacian expansion along the 0 row. We get zeros in front of all our mini matrices, mini determinants, right? Property 3. If one row of A is a scalar multiple, then the determinant of A is what?
0.
It's also 0. How would you prove that?
Row operation.
Row operation. Do a type 3 to kill one of the rows, right?
Yeah.
Right, so, for example, if A equals the determinant of, say, 1, 2, 4, that's equal to 0, as well as the determinant of that's also equal to 0, because this guy is a product of a scalar multiple of that one. Here. This is the property.
So I think you could trick us on the exam with that.
Come again?
So you might trick us on the exam with that then.
No, I don't trick people on exams. What are you talking about? Exams are always straightforward. What are you talking about? Don't say that on camera. People think I'm like an unfair person. I never try to trick anyone. So any times 1 is a multiple of another row, determinant is 0. Why? Because I can use a type 3. I can say replace row 2 by row 2 minus 2 times row 1, and then I get a whole row of zeros, and then I'm back into that situation.
Yeah, the Laplacian expansion
Right?
will immediately. So
What was property 1?
Property 1 is just the identity.
Oh, okay.
Determinant of identity is 1. Right? Sort of obvious, but we're going to list it anyway. Because it's a diagonal matrix, you just multiply along the diagonal and you get 1. We're building up to something here. Right? There are certain problems on the files which I'm going to do a couple of examples, but you have to know all these rules to actually do them. There is one more rule and we'll be able to do those, guys, which comes from property 4. The determinant of the product. Of course, we're assuming that it exists, right? Determinants don't always exist. It's just the product of the determinants.
that seems linear.
No, that's not linear.
And it's not linear, but it kind of resembles a linear function.
No, it's not linear. You need linear is something about plus and scalar multiplication. So, right, determinant of a product of matrices is just the product of the determinants, right? A corollary to this, of course, is that the determinant of a to the k is just going to be the determinant of a raised to the k. Right? This is the form we're mostly going to use it in. This is really important. All right? The reason is you can think of this as the determinant of a times a k times. And using induction, you'll know that you can write this as determinant of a times determinant of a k times, which gives you that.
So does this imply that the determinant is exponential then?
Come again?
So does that mean the determinant is exponential in properties then?
I wouldn't say that.
How did you define it then?
How do I define it?
Yeah, in terms of.
I tell you how they defined it. It's going to be the
No.
hypervolume.
I know the definition, but I mean in terms of trends. It follows either an exponential path or linear path or.
No, none.
None?
No.
Okay.
It just has these properties. You just have to know these properties as written.
Okay.
So yeah, there's no really other elementary function that we know of where I can say, oh, it behaves just like this function. It doesn't. It's sort of a weird function. Right? So it means that if I know the determinants of a, and someone asks you to find the determinant of a raised to some power, you don't actually have to actually multiply a's by some time. You can actually just use this shortcut. Yes?
And power is just, you continuously multiply those using matrix multiplication.
Yeah,
K
matrix
times
multiplication.
Right.
Yeah. So example, a squared is just a times a, right? Where this is matrix multiplication. Right? Or, you know, a cubed would just be a times a times a to the fifth is a times a, etc. Right? So if you go on an exam and someone says, oh, find the determinant of a to the fifth, right? You don't want to do this and then find the determinant. Matrix multiplication is going to take you forever to do it 5 times. So they're trying to trick you. You don't need to do it.
I see that's a hint.
Call it what you will. Okay. So let's do an example, mini example. Say you know the determinant of a is equal to 5, right? What is the determinant of a cubed?
5 cubed?
5 cubed. This is just the determinant of a cubed equals 5 cubed equals 125, right? So I don't need to know what a is because I don't need to have to cube it. It doesn't matter. If I know the determinant of the original, I just cube the answer to get it, right? By this property. Okay, so now here's a problem like what you might see on a final. Except on a final, they'll probably ask you to find the determinant. Here I'm just going to give you. Say you know A is a 3 by 3 matrix with determinant of A is equal to 2. Find A, determinant of 3A to the 4th, B, determinant of A to the 5th, C, the determinant of 2A cubed, A transpose, A inverse. So on a final, they might actually ask you to do this determinant, right? They'll give you a 3 by 3 and say, find the determinant, and then you'll do it. And then they'll say, hence or otherwise, find this, find that, right? And of course, if you try to like multiply a matrix by itself 4 times, you'll spend the whole exam. Right? The trick is to not do that. Use the properties that I've told you so far, and these guys actually aren't that bad.
So I have a question.
Yes?
Does it follow the order of operations?
Come in?
Does it follow the order of operations? Like, would you do a to the fourth and then times it by 3?
Oh, yeah. Yeah.
Okay.
Wait, you do that really?
Yeah.
Can't you just do 3 to the 3 times a and do the whole thing to the 4?
No.
Okay.
Because it's not 3a to the 4th.
No, but 3 to the 3rd times a and then the whole thing to the. I see what you mean. Yeah.
Yeah. So it does follow the order of operations. So it's important for you to take the exponential and then multiply by the
Okay.
Okay, so what are these?
Well, 16 times 9.
16 times 8.
27, I mean. 27.
It's 1290.
Determinant of
1296, right?
3a to the 4th is equal to, what would it look like?
48.
It'd be 3 to the cubed, right?
Yeah.
Because there's 3 rows, times the determinant of a to the 4th. Well, that just means 3 cubed times the determinant of a, I know is 2, to the 4th. So that's what, 1 times 16, which is
1296.
so if I did tell you the matrix, you didn't have to actually multiply by 4 times and multiply everyone by 2 and then do a Laplacian expansion.
3 times 3 is 9. 9 times 3 is
27 times
27.
16.
27.
Oh,
Did you
yeah,
compute
screwed
that?
up. Yeah, they want to. No, it's screwed up.
Whatever that is.
Okay.
B. Determinant of a to the 5th. This is just the determinant of a to the 5th. 2 to the 5th. Okay, how about C?
Well, we didn't really know what
2a cubed a transpose a inverse.
we could clearly ignore the transpose.
No, transpose is 2. Same, right? You said transforms is.
Well, the transpose won't do anything to it. It'll do
Well, we know that this is 2, let's break it down. This is 2 times the determinant of a cubed a transpose a inverse, right? How do we deal with this guy?
Well, transpose won't do anything to it.
I mean, 2 to the 4th now, right? We went 2 times 2
So
times
it'll
2
be 1
times
over.
2.
Well, I don't remember what property, but we just multiply them, right? It will be this times the determinant of this times the determinant of that,
Yes.
right? Because determinants distribute across products. Now this determinant of a cubed, I know is what? Determinant of a all cubed. Determinant of a transpose is what?
2.
Just determinant
It's
of
just
Yeah.
determinant of a.
Oh.
And the determinant of a inverse is 1 over the determinant of a. Right? Now remember, determinants are just real numbers, so these are just numbers now. I can do arithmetic, I can cancel this out. So this is just 8 times the determinant of a cubed, which is just 2 cubed.
So can we say that a transpose times a inverse is equal to 1?
Yes, determinant of a transpose of a inverse.
No, but a transpose times a inverse will equal to identity matrix. Can we say that? If you do matrix multiplication of the.
No, it doesn't.
We can't say that? Okay.
So here we have 8 times 8, right? Alright, so this is the kind of question that would come on a final. This would be probably question 1 or 2. Right? The only difference is they might actually ask you to find this determinant in the beginning. They might say, here's the matrix, find the determinant, and then find all these.
So this might be our only linear algebra question?
No, you definitely have more. But a question like this could show up and it would be like one of the first questions.
I forget, on the finals in this class, do we do all the questions or do we just do the first 7 and then the rest are optional?
In part 1 you do all of them usually.
Okay,
And
so
in
part 2,
you
yeah,
choose.
okay. Do
It's
some.
usually 8 or 9 questions, 2 hours, 15 minutes. So roughly 15 minutes per problem. Okay, so that's the properties of determinants. So this gives you a shortcut that if you know the determinant of some matrix, you can know the determinant of any matrix arithmetic operation.
So we're done.
No, we're not done. We have one more thing to do in the determinants chapter. We have to do Cramer's rule. Did this in algebra, but I guess they saw fit to remind you of it.
This is junior high stuff, right?
Huh?
Junior high stuff, right?
Yeah. Do you guys learn Laplacian expansion in junior high?
Yeah.
Well, I learned it in junior high, yeah.
I don't know. I didn't go to school here, so I don't know.
I don't learn matrices in junior high.
Is it true that it's possible for you to like go to high school and not do math? I've heard of people.
No, that's not possible at all.
It's not
It's
possible.
not possible at all.
It's
no.
kind of possible.
It is kind of possible.
Not
What?
like
Just don't
real
go to
math.
class.
You do like
It depends on what school you go to. Because
Yeah.
if you go to
Because
Brooklyn
that's
Tech or Bronx Science or Stuyvesant, of course not. But there are a lot of ghetto schools where you can get through without any math at all.
Because I was talking to someone the other day and they said the last time I did math was grade 9. I'm like, how is that possible? Like when you get high school, you don't do math anymore.
Well, grade
Yeah,
9 is
stuff like that doesn't happen.
Well, grade 9 in the US is the beginning of high school, first year of high school.
Yeah. It's grade 7 where I come from.
Oh, really?
That's where high school starts, yeah. That's when you're big kids. Okay, so let's write this down in a nice fashion. Cramer's rule says the following. Suppose AX equals B is a system of equations with the determinant of A not equals 0. It's very important that that condition is fulfilled.
Matrix?
Yes.
So we have a
Then-
matrix and a vector? I found
What?
I see.
This is the coefficient matrix, this is the solution, right? And of course, let's write this guy as a bunch of variables, right? Like x1, x2, all the way down to xn or something, right? So here I give you a system of equations. I wrote it in a matrix equation form. But your coefficient matrix, when you find the determinant, you don't get 0, right? Cramer's rule says in that situation, the system has a unique solution. If you have the coefficient matrix, determinant is non-zero, you will have a unique solution, right? Moreover, the solution is given by xi equals dxi over d. Here, d equals the determinant of A, and dxi equals the determinant of So remember, when you do an augmented matrix, each column represents one of your variables, right? Those are the coefficients of a single variable. If you replace each column with the B column, and you find the determinant of that, and you do this ratio, that will give you the solution to the system. Let me do an example. Let's say we want to find x plus 2y equals 5. Let's start with a 2 by 2 system. Just 2x plus 4y equals 11. And let me just say, this is something that they'll ask in finals all the time, so pay attention to this. Use Cramer's rule to solve for y only. And then they put in brackets, do not solve for x. Of course, you'll have students who try to solve for everything and waste their time. They always say something like that. All right?
Extra credit.
It's not extra credit, you don't get any credit. Right? You didn't follow instructions. So sometimes especially if they're using Cramer's rule, they only ask you to find one or two variables. Right? So because usually in Cramer's rule they give you like a 3 by 3 system or a 4 by 4 system. It really only amounts to finding determinants. There's no point in asking you to find 6 determinants, right? So they'll just say, just find one of them. Right? So that's the system, which means we can write this as, of course, 1, 2, 3, 4 times xy equals 5, 11. Right? So this guy here is the a, this guy here is the x, this guy here is the b. Right? So b, remember, is equal to the determinant of a. So it's going to be a determinant of 1, 2, 3, 4. Which is what?
-2.
-2. Right? Now, let's say, which one do we want to solve for? Y, right? So it means we need to find dy. You know what dy is the determinant of the matrix you obtain when you replace the y column with the answers column. Right? So remember here, this would be your x column. These guys give you the coefficient of x. This would be the y column. These guys give you the coefficient of y. If I replace the y column with the answers column, I obtain this matrix. Right? So here, so whichever variable I want to solve for, replace the column corresponding to that variable with the answers column. And then find the determinant of that. So now if I find the determinant of this, what do I get?
-4.
11 minus 15, right, so that's -4. This implies that your y is just equal to dy over d. This is going to be -4 divided by -2. Y is going to be 2.
The thing is that this much easier. In junior high, they made you actually memorize the whole system of equations. It's kind of lame. Like,
Memorize the whole system?
like we didn't do matrices. We actually memorized that. I used to say y2 times x1 minus etc.
Oh, like the formula for the
Yeah,
determinant?
yeah, exactly. We didn't do matrices. We remembered the formula. Like,
Okay. And so that would be the answer to the question. Right? So that would be y. They'd never ask you with this with a 2 by 2 system, by the way. I'm just doing this as an example. It's one of the first examples in Cramer's rule, so I stick with 2 by 2s. Right? So they'll give you like a 3 by 3 system or a 4 by 4 system.
4 by
And then
4?
they'd expect you to do the determinants of 2 4 by 4s. Right? So it turns out whatever variable they tell you to solve for, you replace that column with the answers column. Find the determinant of that guy, and then when you find the determinant of the coefficient matrix, you divide them, you get the answer. For fun, let's find x.
cool.
Hey man, stop telling us to find your x. She left and she's not coming.
That's horrible. That's horrible.
Find my x. Okay. How do you find the x?
Or replace the x column with your answer column.
Well, you need to find dx, right? Which is going to be what?
So 5, 2, 11, 4.
Right? So here I replace the x column with the answers column. Right? And then I find the determinant of this guy.
Minus 21.
Alright, so this would be 20 minus 20. What?
22. 20 minus 22 is negative 2.
Negative 2. This implies your x would be equal to dx over d. D I already found. That was negative 2 as well, if I recall. So your x is 1.
Quick question, can we just
And you can actually check. If you plug in 1 for x and 2 for y, you would actually get
Can
this.
we have just plugged in y into that equation and solve for x?
Yes, you could. I'm doing Cramer's rule. I'm doing an example of Cramer's rule. It's a 2x2 system. Of course, there are far more elementary ways. I mean, if you're given a 2x2 system, no one's going to use Cramer's rule. I'm just using an example of how it would be used. Come on. Right? You don't start with complicated examples. You start with simple examples. So you can actually check the answer yourself. And yeah, if I did it the other way, I get the same answer. You know? Little nice things like that. Because I don't try to trick anyone. I'm very proper rule. Okay, and that's basically Cramer's rule in a nutshell. Cramer's rule says once your d is not 0, you will have a unique solution, and this is how you get the solution.
Is there a proof for this?
Yeah, there's a proof for it. I shall not do it. Other than that, there's really no point in doing it artists because they're sort of the same. Let me give you some tips. Obviously, Cramer's rule involved doing a lot of determinants. So tip number 1 is, if possible, if you have a determinant where there are not a lot of zeros, right? 2x2s wasn't so bad, but if they give you a 3x3 and there's no zeros. One thing you can do is use pivotal condensation to help you find determinants. Another thing that can cut down some work for you, if you don't want to do that, another way is to just be sure to do
Laplace expansion?
Laplace expansion along the column corresponding is 2 R's or 1 R, something like that. It's 2 R's, right?
2 hours.
Or 2 hours, yeah.
And I'll just write an example to show you the virtues of the second tip, where you'll see where it actually cuts down on work for you. An example. Say you're given this system, x minus 2y plus 3z equals 1, 2x minus y minus z equals 0, minus 3x plus y plus 4z equals 0. And by the way, Cramer's rule is something that they ask for specifically. They will say use Cramer's rule to do this. If you do any other method, you get 0. But they'll say no credit for any other method. Right? So Cramer's rule is something that you have to know, unfortunately. It's not. Personally, I don't think it's a very efficient method for solving systems, but it is something that they ask for by name. So you have to know it. Right? So let's say we want to solve for x. Right? Applying the second tip means we'll always expand along the x column because the axis for x. Now what would this look like? This would mean that x would be equal to dx over d. Right? Now your dx is going to be equal to what? It's going to be the determinant of, right? You replace this with the x column.
It's 1, -2, 3.
Now, expand along the x column, because they asked me to solve for x. What would that look like?
It's -1, -1, 1,
This is not
4.
a good example to do that. Anyway, let's continue. 1.
Negative.
So you know this would be plus, this would be minus, this would be plus.
Doesn't matter, really.
This is not really going to show you the benefits of the method. Maybe I should
Change it up.
solve for y instead. Whatever you want you to see, because then the zeros are going to kill everything. You won't need them anyway. Okay, so if I want to solve for the y, it means I'm going to expand along the y column, right? So I'm going to go along here. The sign here is a negative, positive, negative.
Don't you have to put
You
the
have to
1,
change-
0, 0 in the y?
Change the solution.
So you have to change the answer.
Yeah, so might as well just change the zeros to 1 or something.
But then it might not be something that it says.
Yeah, I have to change the answer now.
Well, you're smart. You.
I just want to plug in numbers though, because then if I plug in something and by happenstance the determinant is 0, and someone goes on YouTube and says, "Hey, you're giving him an example where the determinant is 0 and you're using Cramer's rule. What an idiot!" Stuff like that would happen to me. I make up random numbers that are going to turn out the system has no solution or something. Okay, let's stay with x. Right? You'll see. You'll be able to appreciate it. So dx will be 1, 0, 0, minus 2, 3, minus 1, minus 1, 1, 4, and okay. Expand along the x. This is plus, minus, plus. So what would this look like? It would be 1 times. Let's write it out. Right?
-1, -1, 1.
Minus 0 times
Doesn't matter.
Yeah.
this one.
Times -2.
Just write it out to see.
-2, 3, 1, 4.
Plus 0 times.
Minus
-2,
2,
3.
2, minus 3, minus 1, minus 1.
-1.
Right? That's what it would look like. Now let's say we go and we want to find the d, right? D would be the matrix, the determinant of the original vector.
Oh, I see. Ah, wow.
2, minus 1, minus
So
1.
in the end, you're only changing your coefficient.
Right. Now let's say again I decide to expand along the x column. This is plus, this is minus, this is plus. Then this would be 1 times what matrix? Minus 2 times
Minus 3.
minus 3 times. Right? So if this guy weren't 0, it wouldn't be so stupid. But if you have a system where you didn't get 0, what do you notice? These determinants, you already computed them. It ends up being the same mini matrices. When you expand along the same column, you get the same mini matrices. So if you already did the work here, just plug the answers back in here. And so you won't have to it won't look completely different. So instead of doing 6 mini matrices, you can actually cut it down to doing 3 mini matrices. It literally cuts your work in half.
Well, actually, it'd be 5 matrices.
So Don't know why I picked that example of 2 zeros, but yeah, especially if you didn't have 2 zeros here, this method would be coming really in handy, because then you'd have a non-zero number here, which means you'd have to compute them anyway. Okay, one more thing. So Cramer's rule says, well, if the coefficient matrix determinant is non-zero, then we can actually do this. We have a unique solution we can find this way. What if d equals 0?
You just said this exists, so.
Right, but how does this solution not exist? Because remember, there are two ways to not have a unique solution, right? You can have either infinitely many, or you can have no solution at all. It turns out that in Cramer's rule, we can actually know exactly which one is which. There are two cases. First case, if all other dxi equals 0, then we have an infinite number of solutions. And that's all you can say, right? If any one of the dxi is not 0, then there is no solution. And that's basically much all you can say. You won't be able to find the general solution from Cramer's rule in this case. You'd have to use one of the other methods. Well, the only other method.
If all other.
Yeah. So if you find, when you replace the answers column by each column, you still get a matrix where all the determinants are 0, then you would have an infinite number of solutions.
Wait, can you repeat that?
Like,
And then
I can give you a simple example because I don't want to keep computing determinants already. So x plus 2y equals 1, and 2x plus 4y equals 2. Clearly this has infinite number of solutions, right? Your d would be equal to 1, 2, 2, 4, which you know is 0 because one row is a multiple of the other. Your dx would be equal to 1, 2, 2, 4, which is again 0. Your dy would be equal to 1, 2, 2, which is again 0. Everyone is 0. All your d's are 0. This means you have an infinite number of solutions. Clearly, I gave you the same line. I just made one a scalar. All points along the line is a solution.
So if
However, if I tweak that a little bit, like x plus 2y equals 1, and then I let 2x plus 4y equals 3, then clearly it's not an infinite solution. Those two will never overlap. The lines are parallel, but the intercepts will be different. So then here your d would be 1, 2, 2, 4, which clearly is 0, but your dx is 1, 3, 2, 4. This would be 4 minus 6, right? Which is minus 2. So this is not 0. No solution. Right? So if your d is 0, Cramer's rule is definitely not going to give you an answer, but it will tell you how your answer is, how you don't have a unique solution. If it's the case where you have an infinite number or no solution at all. And you'd have to actually find all the other
Why
determinants.
is it no solution? Like it has the determinant.
These are parallel lines. They'll never intersect.
Oh.
quick question.
The slope is the same, but the intersection.
What if x is to find the determinant of the x, and we know that that there is 0 for the domain and there's 0 for the d sub x, but there is no 0 for the d sub y?
There is no 0. What the d sub y is what?
Like 1 or 2.
Yeah, then you're in this case.
Yeah, but what if they tell you to solve for the d sub x? I mean, like if they tell you to use Cramer's rule to solve for all the x values.
Oh, well, no, I mean, if they say to use Cramer's rule as a software, they will give you a consistent system where you can actually has a unique solution. They'll never actually trick you and say solve it when it doesn't exist. But they could conceivably ask you to say, based on Cramer's rule, does this system have a unique solution? I've seen similar problems to that.
In which case we just say that.
In which case you say, well, the determinant of the coefficient matrix is 0, therefore there is no unique solution.
And then we just say that d sub x, d sub y, one or both of them is not equal to 0, so it doesn't make sense.
Yeah, depends on how they ask it. If they went on further to say, is there an infinite number or is there no solution at all? Then you'd continue and say, well, if everyone else is 0, it's infinite. And that's chapter 4. So homework for that is due next time. We're going to start chapter 5, which is, it's not as long as chapter 4, so we should finish this by next class as well. We only have like 10 minutes. So let's begin that. So now we know how to find determinants, and we know how to, a lot of shortcuts to help us find determinants of bigger things. Now we're going to talk about inverses.
The last chapter is 6.
Huh?
The last chapter is 6.
7.
7.
We skipped 6.
Ah. So we just have to catch up.
Yeah, this and the other chapter.
That's fast.
Let A be an n by n matrix. Right? Again, inverses is something that only exists for square matrices. Not all square matrices. A determinant exists for every square matrix. Every square matrix has a determinant. The thing is, not every square matrix has an inverse, and we're going to see that. The inverse of A or right, if we're saying it, they just say A inverse is a matrix That's what the inverse is. It's just a matrix that if I multiply it by my original matrix in any order, I get the identity. For any matrix for which this is true, I call it the inverse of A. Right? And it's using the terminology that we were used to from arithmetic, like a half. Sometimes you can call it 2 inverse if you want. Right? 2 inverse is just a half. Right? Because if you take a half times 2, you get 1. 3 inverse is a third. 4 inverse is a fourth.
Often you don't say that.
Etc. What?
Often you don't say that.
Yeah, we don't say that. But that's where the notation comes from. That's why a half, you know, you can write it as 2 to the minus 1. Because you're thinking of it as the inverse of 2. Which means if you multiply by 2, you get 1. The same way, an inverse matrix is just a matrix when you multiply it by the original guy in any order, you get the identity. That's called an inverse. And truth be told, any one of these is good enough. Like if this one works, that one will automatically work. You won't have to worry about it. So let's just so we're clear, A inverse is not 1 over A. Right? There is no division in matrices. Right? For A to A or you don't think of it as a product or a power or anything like that. It's just a note. This is a notation, right? Just like sine inverse. When you see sine to the minus 1, you don't think of it as 1 over sine. Right? You think of it just arc sign, it's an inverse. Same thing is here. Right? A to the minus 1 means A inverse. It's just another matrix that when you multiply, you get the identity. Okay. Let's see here. Definition. A matrix has an inverse is said to be invertible. Or that's the terminology. Right, so if you're reading any literature, or even in their textbook, and they say, oh, the matrix is non-singular, it just means it has an inverse. Right? That's the terminology that they use.
Where did it come from?
I'm not sure. Right. Obviously here, if the matrix is not invertible, it is said to be that's just some terminology. Okay, what else do we have? Another definition that they introduced, well, when you say this definition, it's going to be obvious what the condition for invertibility is. Matrix A is called singular if the determinant of A equals 0. Right? They also call it singular. That we're going to prove, well, we're not going to prove, but we should just know. A matrix A is invertible this is if and only if the determinant of A is not 0. This is an important fact.
Because there's no solution? Because it's like saying 1 is equal to 2, there's no solution, so you can't go back and forth.
I'm not sure.
Well, if there's no solution, you can't go back and forth. There's no way you can inverse.
I'm not talking about solution. There's
No,
nothing
but
to do with solution.
but if the determinant is equal to 0, then
Nothing, just that's it.
Yeah.
Determinant is equal 0, it's non-invertible.
yeah, and if the determinant is equal to 0, then there's no solution. So if there's no solution, how can you do
If we're interpreting the matrix as the coefficient of a system,
Yeah.
which it's not always being interpreted that way, right? System of equations is just one application of matrices. You don't always think of them as the same thing. Just because you have a matrix doesn't mean you think of it as being in a part of the system.
We're
You never
engineers.
actually do that.
How else will you use it?
It's used in other ways. So non-invertible means you will not be able to find a matrix where when you multiply, you get the identity. Right? So it means no such matrix exists. You say it's non-invertible, and that happens precisely if the determinant is 0. So that tells you when you can find an inverse. If you have a square matrix where the determinant is not 0, you can find an inverse. Otherwise, there is no inverse.
And obviously it has to be square because you can't do the determinant unless it's
Right.
square.
You need a determinant to find you need a square matrix to find a determinant. Right. Okay. So I'm not going to start the next section where how to find the inverse. We start that on Wednesday, but just to mention This is just a note I put in because I noticed that students actually did this in exams. If on an exam you are asked to find the inverse the inverses are unique inverse of a matrix.
It'll always exist.
If they ask you to find one, assume it exists, right? So some students will be like, well, it doesn't exist, and they start finding determinants. That takes forever. And then they move on to find the inverse. It's sort of, you know, don't waste your time doing that. And use the above equation as end to check your work.
So for our homework, we assume that they all exist.
Yeah, if they ask you to find it, it exists.
In the homework too.
Yeah. But the homework for this isn't due yet because I didn't actually show you how to find it.
Ah, sure.
But the homework for chapter 4 is due next class, and we'll finish this up next class. And the test is next Monday. All right, the last test is next Monday. Yes. I believe it's the 23rd.
Any more quizzes or no? No more quizzes, right?
So that's